All right, and having discussed those major theorems and getting all of our tools lined up, I think we're ready to finally do some examples. So here's our first example that we're going to work through. So we're given a vector field and a path, and then and a parameter and a restriction for the path. And so we want to compute the vector line integral in three different ways. Okay, well, the first way is, well, let's just do it directly. Okay, so that is to say, if we're doing it directly, let's just do integral from 0 to 1 of f of y of t, and then times y, or dotted with y prime of t dt. Okay, and now you pause the video and work on this for 5 hours, and eventually you'll get down to an answer that is negative 33 over 2. Okay, I'm not saying 5 hours, but it does take quite a while. Okay, so you can do it that way, do it directly. The e to the t minus 1 here in the path, that gets to be a little annoying to work with. So you can do it, or have Wolfram Alpha do it. Okay, second way, let's maybe be a little bit smarter, and so if we know we have a vector line integral, maybe we can use the fundamental theorem of line integrals, but we need some assumptions with that, or we need to check some assumptions. So first of all, I need to be careful with my domain. So my domain here is R2. Okay, what do I know about R2? R2, this is open, and closed, and it's also connected. Okay, so that's good. So it's meeting some of the requirements of FTLI. The other thing that I need is that F is C1. So this is literally the work that I would need to see in your homework if you're going to use FTLI from here on out. Okay, so in terms of most of the requirements, we've met most of the requirements of FTLI, of the fundamental theorem of line integrals, but I need to find that potential function f. Okay, so potential function, okay, f, and maybe if I look at this closely enough, I can tease out something. What if we kind of do those procedures that we did last week, and so we say this is 3x squared over 2, and then plus 5xy, okay, and then I'm probably going to have a plus 7xy squared over 2, okay, and then will that work? And so I want you to pause and verify that that will work for our given vector field. And it ends up working, so you can always include enough work to prove to me that it does work. And then we're going to say that this parameterizes from, and then if we put in 0 for t into our path, or I'm sorry, yes, if we put in the bounds here, we're going to go from 1, 3 to 5, 2. Okay, and then so we will have that this integral, this vector line integral, is going to be the same as f of 5, 2 minus f of 1, 3, and you end up getting the same negative 33 over 2. Okay, that's nice. All right, and then the last thing that we can do, or another way we could do it, there's many different ways, but we can still notice that, okay, so still the domain is R2, which is open and connected, okay, and in fact, I'm actually going to say it's simply connected. Okay, since I'm not removing anything, this is simply connected, which is really good. And also f is C1. Okay, now why do I care about simply connected? Oh, well, I can use that derivative matrix of our vector field. So I can note that df, okay, if I compute this, I have to make sure it exists, and I don't really care what the diagonal elements are, but I want to make sure that those off diagonals are the same, and they actually are. So this is going to be symmetric, and then as a result, this is going to be that f is path independent. Okay, and so maybe instead of using that ugly path, maybe instead I'm going to use a nicer path, call it x of t, and maybe if I just get rid of the e to the t minus 1, my life will be a lot easier, and it ends up that I can, and then I'm just going to say that t is within oops, 0, 1. Okay, so since it's path independent, as long as I meet those endpoints, I'm golden, and this ends up working just as well. Okay, and then you can go on and use kind of this first approach with this new path, and that'll be a lot easier for you. Okay, but that's going to wrap up this video, and so we're done with example 1. We'll move on to example 2.